Hello and welcome to another video. In this video, we're going to be working on maximum profit and job scheduling. And in the problem, you have n jobs where every job is scheduled to be done from start time to end time, obtaining some profit. You're given start time, end time, and profit arrays. Return the maximum profit you can take such that there are no two jobs in the subset with overlapping time range. If you choose a job that ends with time x, you can start another job that starts at time x. Now, let's take a look at the examples. So in this first one, there are 4 jobs. So they say you want to take the first and fourth job, so you can take these two and you'll have a profit of 120, and then they don't overlap. In the second one, you have some more stuff. So you want to take the first, fourth, and fifth job, and here they are, so they don't overlap, and the profit is 150. And in the third one, they all overlap, so you just want to take the one that gives you the most, which is this one over here. So I think the intuition for this problem is pretty straightforward with these like jobs things. Like basically the idea is you want to get your problem down into, you want to look at the constraints first, but you want to essentially get your problem down into take or don't take a job, ideally, right? So you have some kind of like index in your jobs, and then you just choose like, if I take it, where do I go? And if I don't take it, where do I go? And then figure out like what kind of states you need for that. Kind of like the same thing with coins, right? If you're like use a coin, don't use a coin. This is like a very common type of problem where you have like, I think it's called like a bounded knapsack problem, where essentially you have a bunch of things you can take or not take. You have a limited number of them, and that's kind of how you want to do it. So let's take a look at the constraints. So the array is 5 times 10 to the 4th. So we really want to figure out like, if we choose to take or not take something, what would that look like? And yeah, I think this is pretty straightforward. This is going to be DP because you essentially have choices that rely on each other. And if you take a job, then like you have to not take some other jobs and so on. So I think it kind of makes a lot of sense to use DP here. I think there is like another solution with a heap, but it's not super intuitive. I think this one is very intuitive. So let's talk about this one and some optimizations. So essentially, what we want to do is we want to, like, all these start and end profits have to be in the same index, right? So we can take all of our arrays and just make an array of tuples. So essentially, every single array will have a start, end, and profit. And in Python, you can just zip up your 3 arrays. So basically, it will have this, right? And the other thing is, in these examples, these start indices were increasing, but that's not guaranteed. So the start indices are going to be all over the place. So you're going to want to sort your arrays by the start index, because that would make sense, right? Or by the start value. Because if you choose to start a job at some time, we have to figure out, okay, when are we going to end that job, and like where do we traverse? If all the start values are all over the place, it's kind of hard to do that. So essentially, you make an array of tuples where each tuple will be the start and profit for your particular job, and they are lined up like they all have the same length. So essentially, for something like this one, it would be like a tuple of 1, 2, 5, and then 1, 3, 6, and then 1, 4, 4, and you sort it by the start time, and then the second value should be your end time. So when you sort it, it'll be like this. Like this will be first, this will be second, this will be third, which is what you want, right? You always want to take, that's the easiest way to do it. I think actually the second value doesn't matter too much, but you do want to have it sorted by the first value. So like if the second value was the cost or the profit or something, it doesn't really matter. But so now that we have something like this, what do we need? Like let's figure out like what would happen here. Like let's say we are at this job here. Like what would happen if we take it or don't take it or something? So if we don't take it, it's kind of obvious. We just move on to the next job in the array, right? Because they are sorted in increasing order. So if we don't take this job, we just recurse down over here. But what if we do take the job? So when we do take the job, we have to look at the end time. Well, first we have to actually add the profit, right? So we add the profit, but then where do we recurse? So we have to look at the end time, and we have to find the first job that satisfies this end time, because we want to ideally be able to take every job possible. So the first job that satisfies this end time, so if this ends at 2, they said in the description that if it ends at 2, we can take a job that starts at 2 and that doesn't overlap. So ideally, we want to recurse here, and that's why this being sorted is going to help us a lot. And so let's say we were at some other random job, like let's say we're at this job, and we choose to take or don't take. So once again, if we don't take, pretty straightforward, we just move on to the next one. But if we do take, we look, where does it end? And let's say let's change this a little bit. Let's change this value. Let's say this ends instead of 2. Let's say this ends at, and this can happen. This can easily happen. So let's say this actually ends at 10. So what you could do is you could manually like look through like, okay, where's 10? Where's 10? Where's 10? Where's 10? Like, what's the first number that's greater than or equal to 10? Oh, here it is. But then imagine every single job you have ends at 10. Then at every single one, you'd have to go all the way to the end. And that would be, if you want to think about the time complexity, so if you have index as a state, and you also have a for loop that goes, you know, worst case all the way to the end, it'll be like index squared, which isn't going to pass, right? Because this is 5 times 10 to the 4th, so you want an n or n log n solution. So this is where we can take advantage of the fact that we sorted our start times, and it's very convenient now, because we can, like, for example, if we know this ends at 10, we can just binary search for the first index that is 10 or more. And then this would be a logarithmic time, right? So now our stuff in our DP function would be log n. And our DP function goes through n indices. So this would be fine, because this would be like 50 times 5 times 10 to the 4th or something. So this would be totally fine. So that's kind of the idea behind this problem. So let's actually write down our like official DP stuff. So for DP, you need state. So like I said, for state, all you need is an index, just where you're at. Base case should be pretty straightforward as well. Out of bounds, return 0, right? This is pretty common. Once you have no more jobs to take, you just want to return 0 because there's nothing else. And then recursive, take or not take, right? So that's that kind of DP problem. It's yeah, like I said, I think it's called a bounded knapsack. So if we take, then we just take profit value plus DP of the index, leftmost index, that is greater than or equal to end time, right? So like I said, if this ends at 10, we would find the leftmost index. We want to be able to take as many jobs as possible. We want to have the option at least. So for example, if this ends at 2, we want to go to this 2, not this 2, even though both of these are, or this 2, not this 2, because we want to have the option of taking this job, and we want to have the option of taking this job. If we just go to here, then we never have the option of taking this job, and for all you know, this could have been better. So take the leftmost index that is greater than or equal to end time, and don't take is the really easy one. So don't take, just go to DP of I plus 1, right? And you just want to return the max of these, because they ask you, like, these kinds of things change problem by problem, but the template is the same. So they ask you, like, what's the max profit? So your options are take the job or don't take the job. If you take the job, figure out where to go. And if you don't take the job, just move on to the next one. And that will pretty much do it. And then we can just have like a recursive helper function that will take in whatever index we're at. So let's say we are here. So we can just pass in, for example, like let's say we're here. Let's say this ends at 10. We can just have a recursive helper function that will take in the index we're at, right? And the end time of the job. And then we know that the, like, where our value can lie is going to be in index plus 1, right? So if we have a left and a right for a binary search, left is going to be index plus 1. In this case, it's going to be 3 because it has to be over here, right? Because our jobs are sorted in started order, and we've already looked at everything over here. So our left is going to be here, and our right will just be the end of the array. So right will be 9. And we basically search for here, find a value that is greater, find the leftmost value that is greater than or equal to 10, and then that's what, or we want the value, we want the index. So find the leftmost index of the job that is greater than or equal to 10, return that, and that's where we want to recurse to. And if we don't find anything, like let's say this starts at 9, if we don't find anything, we can just return 10, and then we can recurse to 10, and that'll be our base case, right? Where we're out of bounds, so we can't take any more jobs. So I think this is not like too bad of a hard problem, to be honest, even though you do have binary search DP, just because I think it's very easy to figure out like the parameters for the DP. It's not like super unintuitive or something. So we can code it up now. So we're going to make a length of this thing. So we can say length. And I'm going to use in Python, you can make a zip. So you can just make a bunch of tuples like I was saying, and then you can sort them by the start time. So you can say joins equals, we want to sort it, and we want to zip start time, end time, and profit. That way, they will all be together in tuples, and then we will sort by start time. Then we have a cache, and we will make this helper function called next job that will just take an index and a time that our current job will end, and will return us the index we want to recurse to. So we can say def next job. It will take an index and a time. And I'm gonna pass, like in the DP, I'm already gonna pass like the current index plus 1. So we can just make the left equal to, or actually, no, I'll just pass the current index, I think is fine. So we'll just make left, right equal to I plus 1, right? Because I is going to be the index of the job we just took. And then right is going to be the length of this thing minus 1, so s minus 1. Then we can make our result equals s, and this is what we're going to return. So if we don't find a job that matches our criteria, we will just return the length of start time, which will just be the base case. So now we just do a normal binary search, and I think I talked about this. I really like this template as opposed to like this kind of thing. And I like having a result variable because then I don't have to worry about like, do I return left, right, or left minus 1 or whatever. It's a lot easier. Get a pivot value. So basically, if joins at the pivot value, and remember, it's this joins is going to be a tuple of start, end, and profit. So we want joins at the pivot value, and then we want the start time, so 0, is greater than or equal to time. That means this is a valid start location, so we will mark it. And we want to see if there's anything better, and by anything better, I mean, is there anything to the left of it, right? Because we want the leftmost start time that's greater than or equal to our end time. So we will go left here. Otherwise, our start time is not big enough, so we want to go right. And then we can return the result here. And so the result, like I said, if we don't find anything, this will just be the length of the string, which is totally fine. And then that will, or not the length of the string, it'll be the length of this join thing, which will be our base case. Okay, so now we can have our DP function. So def DP, it'll take an index. So we have our base case, right? If index equals s, which is the length of the whole thing, return 0 because we have no more jobs left. If index in cache, we return cache index. And finally, we have our recursive case. So cache index, we have two choices, take or not take. So this is going to be the max of, so let's do the take first. So this is going to be, take is the profit that we currently made. So this is going to be joins at index. And remember, it's start and profit. So this is going to be at index 2 because it's a list of tuples now that's sorted by start time. Plus DP, where do we want to recurse? We just want to call this next job function. So we want to call next job. We want to give it the end time of our current job, which is joins index 1. I could have probably separated this out into variables for legibility, but this is fine, I think. So this is going to be the end time of our current job, and then we want to pass in the index of our current job, which is just index. So we'll pass in that, and then the binary search will start at the index after our current job. Okay, so that's one case. Now we have the other case of not taking the job, which is just DP of index plus 1. So that one's pretty easy. So like I said, with this binary search, and we now optimize this inner loop, we don't have to like look for the next job manually one by one, because worst case scenario, imagine every job ends at like 1 million or 1 billion or whatever. You'd have to loop like it would be an n squared, which would fail. Yeah, so now we just return cache index. And finally, we just need to call this DP on index 0. So let's see. Okay, if joins P0, oh, is this? Okay, I think we got it. Yeah. And they're about like all the solutions are kind of close, so this is pretty good. And yeah, like I said, you do have to sort your, even though they don't tell you, you do have to sort your start times, because when I tested this, like if we actually get rid of the sorted thing, they do give you start times that are in all kinds of random orders, which wouldn't make any sense. Like ideally you want to start at the earliest job possible, take or not take, and then you recurse, right? That's going to be the easiest way to do it. I don't think it's going to, because in order to do a binary search, you have to have a sorted array, right? So because we're binary searching through start times, if they're not sorted, this wouldn't work at all. Like we'd have to manually look through in that case. And like I said, I do think this is like not too bad, because even though you do have to do a DP and a binary search, the binary search is really obvious, I feel like, and the DP state is also really obvious. So the hardest part about like hard DP problems is that the states are like very unintuitive. Like you have to do some weird stuff like splitting a string or like some balloon problem or something where like you have to it's really unintuitive, where I feel like for this it's like pretty straightforward. Okay, so for the time, this is going to be n log n, because obviously we have a sort to start, and then we have this binary search every single time for every index. And the space. So we did create this like zip thing. I think you probably, well, yeah, I mean, you could modify it in place. So you could probably get away with doing something else. Like you could modify it in place, obviously, which isn't great. So I do think you kind of need this thing. But either way, you have a cache, which is O of n anyway, right? This can be for every index. So regardless, even if you didn't zip these, you still need the cache. So this is just going to be O of n space. And yeah, I think that's going to be all for this problem. So hopefully it was helpful. Like I said, not too bad of a problem. And if it was helpful, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.